Okay, so let's just first go around. I just want to know, I mean, all of you are here typically because you're going to do med school, right? So what kind of medicine do you want to practice is what I want to know. All right, Jocelyn, what's up with you?
I'm not sure yet.
Not sure.
Yeah, and for the MCAT, I don't have any intentions of writing the test, so maybe like next year in fall.
You're going to do what now?
The MCAT,
You're going to take it
next year in fall.
Okay. They recommend that you take it this summer. That's what Dr. Roach recommends, by the way. If y'all are sophomores, or some of you are sophomores, some of you are juniors, but some of you are sophomores, this should be the first time.
You take the MCAT?
That's what Dr. Roach just said. She told me sophomore. But
You're supposed to take it twice.
yeah, so so that way you can get yours, you can take it again, because you'll probably want to take it.
I want to do naturopathic medicine, and I'm not entirely sure.
Like a DO kind of thing?
Yeah.
Okay.
And I'm not entirely sure if I'm actually going to take the MCAT to get to the schools that I'm looking at, so I'm just trying to prepare.
Who's that I know just did DO? Is that Andrew? Not that one. Is that Andrew? I think he's not that one. Not one to say. Surgeon?
Not culture right now, it's just physiology.
Okay.
Just general medicine. Anesthesia and pain management.
Okay. All right. Well, that's very exciting. I think I just saw like one of my former students, and she's a doctor now. That's really cool to see. I mean, it's been like 8 years since I've had her, but I guess it takes that long to go through med school and all that. But I know this class sucks too. Okay, it's not really supposed to be fun for you because it's like a fire hydrant. And not only that, but it reminds you of everything that you missed in those classes that you've already had, and it sort of makes you feel like, well, I didn't get anything out of that class, but every little bit helps, okay? And we're going to go pretty fast through this stuff, through chapters. We'll probably do a chapter or more a day. I have you for 4 meetings, so we'll try to make it as far as we can. Okie dokie? All right, well, the first chapter is on kinematics. They also have some initial stuff about just units and vectors and stuff. It will help you to know your units, right? So don't forget your basic SI units that we have: mass, length, and time. Okay, let me fix this. It's going to go me sticky. I'm sorry. Mass, length, and time. Mass is in kilograms, length is in meters, time is in seconds. And then we also have some others, like current, which we're seeing now. This is in amps, or particularly in coulombs per second. So current isn't really a basic SI unit. It's not a base unit where it's just an individual measurement, but it's actually dependent upon coulombs and seconds. And then we also have amount, temperature, and luminous intensity. So amount, if I want to know what amount I have of something, like money, for example, I have 1 mole of money. See, that would be a lot of money. I don't really have a mole of money, but that would be a lot, because a mole is a lot. And temperature, which is in Kelvin, and the luminous intensity, which we might get to, hopefully we will, to using it, is in candela, or sometimes called candles. And then we have those basic units can make up more complicated units, like for example a Newton, which we know is a force. A Newton is a kilogram meter per second squared. I think that often the MCAT uses SI units, but you might encounter some British units as well. And they have a table with the British units for mass and length and force. Like, for example, pounds is for force, whereas we use newtons. The slug is for mass, whereas we use kilograms. But usually on the MCAT, you'll see SI units. There probably aren't going to be any questions about units. I haven't seen any in any of the practice tests that I've seen. But certainly knowing your units and knowing how to deal with units will help you a lot. So, for example, we did this back in Physics 1, where we take an equation and we break it down by its units. So for example, let's say that I have an equation VAT over X, and I want to know what those basic SI units are. I can do just dimensional analysis on that, where I have meters per second squared, T is seconds, and then X is meters, and I do 1 over meters because it's, you know, in the denominator. And then I can cancel out some things here. The meters cancel, 1 of the seconds cancel, and I'm just left with meters per second squared. Just knowing how to deal with your units will help you in taking the exams, because if you're dealing with equations, you'll know if they're correct just by checking your units. So just being quick with units will help you in a lot of different ways, but probably not going to encounter questions that are just particularly about units. Now you probably will encounter questions about vectors. And let's just look quickly. We're not going to do a whole lot of time on vectors, but you need to know how to graphically add vectors and how to numerically add vectors. And then I'll show you some clicker questions in just a bit where we deal with those. So let's say that I have a vector A and I have a vector B, like that. If I want to take the vector sum, remember to take the vector sum, I use this tip to tail method, where I draw the first vector A, I draw the second vector B, like that. I imagine that's the same as what I just drew. This is A, this is B, and then the sum of those, I begin at the tail of the first vector and draw to the tip of the second vector. So this red line represents the vector A plus B. Okay? If I want to do A minus B, if I take the negative of a vector, negative B is just the same magnitude as B, but in the opposite direction. Remember, our vectors have a magnitude and a direction. So the magnitude is represented by the length, the direction is represented by the direction of the arrow. And so if I'm doing A minus B, that's going to look like this. I'll have the vector A like this, vector negative B like that, and then the difference, A minus B, looks like that. Okay? You also need to know how to add them numerically. So if I have a vector, say that is 5 meters at 30 degrees above the x-axis, and I want to add it to a vector that is 3 meters along the x-axis, then in order to add those vectors, I first draw my coordinate system, and then I draw the vectors on that coordinate system. The 5 meter that's 30 degrees above the x-axis will look like this. 5 meters, 30 degrees. And then the second vector, let's do it in black, 3 meters along the x-axis. I can draw it like this. This is my 3 meter vector. And then the sum of these two will look like that. In order to calculate the numerical sum of these, I find the x component of the 5 meter. So for the 5 meter, which I'll do in blue, the x component is going to be 5 cosine of 30, and the y component of that vector will be 5 sine of 30. Now listen, you guys know you're not allowed to use calculators, but you will see trig functions. They'll usually stick to a 30, 60, or 45 degree angle. So, or you might see a 3, 4, 5 triangle. I made up a little cheat sheet for you here. It's not for you to take into the MCAT with you, like it's not really for cheating. Okay, it's sort of for you to look at, and I'm started putting things that you just need to memorize. Right? You just need to know these things. So you need to know these relationships. These are the original copies, so y'all get the legible ones. And then these, you can't really see, I'm sorry, but I'm going to make another copy of this soon when I start filling in these tables, and I'll put this online. So you can make it out if you look at it and squint, but unfortunately it didn't come out on the copier very well. All right, so you need to know just these. The sine of 30 degrees is a half. The cosine of 30 degrees is square. No. The cosine of 30 degrees is square root of 3 over 2. The tangent of 30 is 1 over square root of 3. That sort of thing. You're going to have to be quick, okay, because you have to know how to deal with these numbers. And on the MCAT, a lot of it's just about doing approximations, right? Taking 9.8 to 10, taking 1.6 times 10 to the minus 27ths to 2 times 10 to the minus 27ths. And working with those numbers a lot until you can figure out what is the right answer. You'll see that as we work through some problems, tricks into not using your calculator. So as you're working through the practice tests and the practice questions and stuff like that, don't use your calculator, okay? That's hard, right? It's like an old friend. You ever see that YouTube video of the high school student that took her calculator to the prom with her? She dressed him up, put a little tuxedo on it, took it to the prom with her. Okay. All right, so here 5 cosine 30, our cosine 30 is square root of 3 over 2, so it's going to be 5 square root of 3 over 2. Our 5 sine of 30 is going to be 2.5. So those are my x and y components. And then also notice that the square root of 3 is about 1.7. So this is going to be about 2.5 times 1.7. We'll come back to that. So those are my x and y components. What's 2.5 times 1.7? Well, let's see, it's 3.4 plus half of 1.7. Now follow what I'm doing. 2 times 1.7 is 3.4. Plus a half of 1.7 is 0.8. So it's 3.4 plus 0.8 is 4.2. So those are my x and y components. And for the other vector, the x component only is 3 meters. And then if I want to find the, I can redraw these now as just the x and y components. So I get 4.2, I get 3, and I get 2.5. Okay. Now I know that my resultant looks like this. It's going to have a distance that is the square root of 7 squared plus 3 plus 2.5 squared. And so if I round off that 2.5 to 3, it's like 49 plus 9, which is, you know, the square root of 58, which is approximately equal to 8, because 8 squared is 64. So it's approximately equal to 8. You need to be really good with those approximations, doing that math in your head, okay? Y'all are okay with that? You shall be okay with it. As your practice, just, you know, make sure that you do that along the way. And then the angle, you know, it's hard to do this trig function in your head, but we know that this has to be less than 45 degrees, right? So that can whittle down the answers a lot. In fact, if we look at this, this is a 3-7 triangle, and we know that a 3-4-5 triangle, this angle would be 37 degrees. So in fact, we know this has to be less than 37 degrees even. Y'all follow that special triangle? You need to know it like an old friend. If I have a triangle that is a 3, 4, 5, then this angle is 37 degrees. It's off at the small side. This angle is 53 degrees. So those 3 special triangles are on the top of the page. You need to know them, like I said, like old friends that you meet every day. Okay? So take that and just paste it to your bathroom mirror, wherever you want to put it. You do need to know how to add up vectors, you know, like this. Okay? Let me show you a couple questions. I have a handout for you with some questions that are similar to these. So I have my widths about me. I'll probably send this out a couple days ahead of time to let you print it. But usually I won't have my widths about me, so I'll just photocopy it for you and bring it. Is that okay? We're probably not going to do all these questions, but we'll do what we can. All right, so let's do this first one. Which of the following, I'm not sure where this is on that page. It might be on the back. Just flip around until you find the page that looks like this. Which of the following represents the vector sum of Q and R? Looking at this one right here. Which of the following represents the vector sum of the vector Q and the vector R? There's Q, there's R. Which of these represents the sum of them? Go ahead and click in with your answer. Oh, all right, a few more seconds. 32, I'll stop. Okay, awesome. A is right. So Q and R, if I draw Q, draw R, the vector sum looks like that. That's A. Common mistake is to draw Q, there's Q, and then draw R like that. That's not the right answer. Okay? You draw the first vector here, draw the second vector from the tail to the tip. That's your resultant vector. Which of the following could not be a pair of component vectors for Q? Remember, every vector has both an x and a y component. So which of these could not be a pair of component vectors for the vector Q? There's our vector Q. Which of these could not be the component? 3 of them are correct. 1 of them is not correct. Which one is not correct? By the way, these questions are from like old practice exams from the MCAT. It's not just something I cooked up. All right, just a few more seconds. 54. Awesome. C is right. This is my vector Q right here. Notice I can have Q there. I can have Q there. Oh wait, no, C's not right. Jump at C. Yeah, the answer is B. Because notice C here, if I move, I have this vector here, and then I take this and I move it down here, like that. I can translate vectors around, and so then that is the vector Q. See, this vector that I've drawn is identical to that one. But notice here, there's no way that I can get these vectors to look like that. Those vectors added up are instead going to look like that. There's no way for me to draw them to produce the vector Q. This, in fact, is equal to negative Q. B is. So B is the right answer. Good job, one of you, whoever that was. But that's a little tricky. Remember, you can translate your vectors to any place in space as long as you don't change their magnitude or their direction. Okay, in your book they talk about multiplying vectors. There are 2 ways, actually there are 3 ways you can multiply vectors. You can multiply them by a scalar. So if I have a vector and I multiply it times 2, I just make it twice as long. I think we sort of have that intuitively. And then there are other 2 ways that you can multiply vectors. You can multiply them by other vectors in the parallel direction or in the perpendicular direction. This is called the dot product and the cross product. Neither of which y'all have seen. You get to this in like calculus 3, which I don't take, I'm pretty sure. No calc 3, right? But we've seen them. We saw it. The dot product occurs when I multiply a vector times another vector that's in the same direction. We use that with work. So that comes up with work. The dot product is one vector times another vector that's parallel. So for example, if I have a vector in this direction, I'll call that A, and then I have a vector in this direction, I call that B. And if I want to take the dot product, what I want to do is multiply the magnitude of this vector times the magnitude of the vector B that is in the same direction as A. Now that would be the x component, right? And so the dot product is going to be A times B, the magnitude of A, times the magnitude of B, times what do you think? Cosine or sine of theta between them? It has to be the cosine, right? AB cosine theta. That is the dot product. This is called A dot B. It's AB cosine theta. That's what we did with work. When we were doing work, really we were taking the dot product of the force vector and the displacement vector. Remember the work was FB cosine theta? We'll see that on Monday, by the way. That's in chapter 2. The other thing is the vector product, or the cross, let's call it the cross product, the cross product this multiplies two perpendicular vectors. So for example, if I have vector A and B, I want to take the cross product. The only difference here is instead of having AB cosine theta, if I want to multiply A times the component of B that's perpendicular to the vector, what do I do here? I use the sine. Okay, so the cross product would equal to A times B times the sine of theta. Do y'all remember any time that we wanted to multiply two vectors that were perpendicular? This will come up today, hopefully, if we get there. Two perpendicular vectors. Oh. No, not like that, no. When we found torque, remember torque was the length of the moment arm times the force? We were looking for a perpendicular force. And so when we found torque, we were actually doing the cross product. I haven't seen many questions about this, but let's, in old practice tests and stuff, but this is a little question about it. Which of the following is true if the product of vectors Q and R is a scalar? Oh, and also another thing, let me finish this. The dot product is a scalar quantity. Remember, work is a scalar quantity. The cross product is a vector quantity. Let me write that down. The dot product is scalar. Remember, work, which was a scalar quantity. The cross product, on the other hand, is a vector. Remember, torque. We didn't really treat torque as a vector, but it really is a vector quantity. It does have direction. All right, so cross products are a vector, dot products are a scalar. All right, so which of these statements is true? Goodness question. Which of the following is true if the product of vectors Q and R is a scalar? Just a few more seconds, I'll stop. At 125. Okay, good. A is right. That the vector product have a magnitude proportional to the cosine of the angle between Q and R. Okay? That's good. A lot of the MCAT is really just about reading the questions and stuff, but you really have to know the material too. Like if you don't know what a dot product is or a cross product, you're not going to be able to read a question like that and figure out what the answer is. So it is true that in the MCAT you have to be able to read really well because we have some long passage questions, and I'm sure that y'all are familiar with some of those and we'll do some, but you also have to know the material as well. Okay. All right. Let's move away from vectors then, and we're gonna skip the right-hand rule. Your book does go into the right-hand rule, and you might want to read that, but we'll come back to it when we get to electromagnetism. But let's go straight into kinematics. So we have some things we need to define. Displacement. Remember displacement, which we'll call, what does your book call it? They call it, yeah, they just call it x. It is a vector quantity, and it's equal to the final position minus the initial position. X final minus x initial. It is a vector. In contrast, distance is just the total distance traveled. And those might seem like the same, but they're not really, because like if I start here and I move here, I've moved 2 meters to the left, so negative 2 meters to your left, whereas my distance isn't negative 2, it's just going to be 2. And then also, like if I start here and then go over here and then I come back over here, my displacement is 0 because I'm returning to my initial position, but my distance is actually 3 meters or whatever it is that I moved. So understand the difference between displacement and distance, and that does come up in some questions that you just understand that. Also the velocity the velocity is defined as the limit as delta t approaches 0 of delta x over delta t. So this is a differential or a derivative. As delta t gets really, really small, then you approach the instantaneous velocity. As you let this time interval get really small, then you approach the instantaneous velocity. Notice if I leave off this limit, this is something called the average velocity. So the average velocity is delta x over delta t. We usually call this v bar. It's going to be delta x over delta t. The average velocity, as we'll see, is dependent only upon your initial and your final position and averaged over that time. So if I were to plot x versus t like this, and I want to know my average velocity between this point and this point, it would just take into account those 2 points. This position minus this position divided by the time elapsed, and wouldn't take into account all the stuff that happens in between. The instantaneous velocity, on the other hand, if I want to know the instantaneous velocity, say, at this point, it would just be the slope of that tangent line at that point, the derivative of this function at that particular point. All right? Remember, my distance versus time graphs, or my x versus t graphs, the slope of these equals the instantaneous velocity, or the velocity at a particular point. The slope at a particular point is the instantaneous velocity. Your book doesn't really go into that, but I have seen some questions with graphing, looking at plots of motion and being able to interpret them. The MCAT's really big on interpretations. They have a lot of calculations too, but just interpreting graphs and interpreting data and stuff like that, MCAT's really big on that sort of thing. All right, and then finally, acceleration. Oh, let's see, they do acceleration here? Yeah, they do acceleration later. Well, let's go ahead and add in acceleration here. I really do like this book. Do y'all like it? Y'all used it very much? Yeah. You should be reading it, okay? Read a couple of chapters a week. So for our acceleration is equal to the limit as delta t approaches 0 of delta v over delta t. Where here my delta v over delta t, this is my average acceleration. So just like we had here, if I replace this with a v, I would average over a certain time interval to say what is my acceleration, where it would just take into account the final velocity and the initial velocity. And then as I let that delta t get really, really small, when I take this limit right here, then that gives me my acceleration at a particular instant. And that's the difference between instantaneous acceleration and an average acceleration. Remember, if I have a graph of acceleration or velocity versus time, the slope of this graph equals the acceleration. What does the area under the graph represent? Y'all recall? Distance traveled. Not displacement, but distance traveled. So this represents the distance traveled. Let's do a couple questions about that. Let's see, where were they? Sorry, my questions are sort of jumbled up. Before we do this, let me go ahead and give you some equations. These are actually on your little memory sheet, but in the book they give these kinematics equations to you. No, I'm sorry, we're going to hold off on that. Let's go ahead and do these other questions then. Let's look at 69 here, 68. Okay, let's do 69 first. If the graphs shown here are displacement versus time, that is to say that this is displacement, this is time, which of those represent a particle with positive velocity? W, x, and z, w, x, and z, or do all of them represent particles with positive velocity. All right, just a few more seconds. I'll stop at 40. C is right. I can understand why you put D, because you think, well, gosh, doesn't the Y graph, have positive velocity? But it's zero velocity and not considered a positive value. So the slope here gives the velocity. Here, I have a positive slope. It is an unchanging slope, so I have a constant velocity. Here I have a positive velocity as well, but it's increasing in magnitude because the slope is increasing. Here I have a positive velocity that's decreasing in magnitude, slowing down, and here I have zero velocity. So this one is technically not positive, it's zero. So what's that? W, X, and Z. Which of these represents, number 68, which of these represents a particle with positive acceleration? Looking at this one, which of these, there's still displacement versus time, which of these represent positive acceleration? A few more seconds. Just guess if you're not sure. Stop at 42. Okay, let's see. Positive acceleration. Remember our rule from Physics 101 that if the velocity is in one direction, you're increasing, then the acceleration is in the same direction. If your velocity is in one direction and it's decreasing in magnitude, the acceleration is in the opposite direction. So let's see what we have here. The velocity is positive and increasing. Positive acceleration. The velocity is positive but decreasing. Acceleration is what? Negative. Here my acceleration is, and here it's also zero because the slope is unchanging. So the graph that represents a particle with positive acceleration, gosh, I guess that's just X only. So B is the right answer. Let's try 66. Displacement versus time graphs, the slope represents what? All right, just a few more seconds. 23. Probably gonna stop now. Looks like you're all in. Awesome. C is right. Sorry, no jokes for you, even if you're 100%, because you already hear all my jokes. And I'm sort of running low on jokes, honestly. I gotta get some new ones. Middle of the second semester. All right, 75. The area under the curve represents what? We haven't seen this, an acceleration versus time. What does the area give us? Think about that. All right, I'll stop at, right now, I guess. Okay, let's see, you're sort of all over the board. The area under the curve, well, if I think about an acceleration versus time, looking at the area, remember the area is just one side times the other, so it's going to have units of area times time. That's meters per second squared times seconds. So that'll go cancel, and I'm left with meters per second. So C is the right answer. Again, not something that we've seen before. We don't really use an acceleration versus time graph very often, because usually we're dealing with objects that have constant acceleration. It doesn't change. All right, we'll come back to 124. All right. Now let's look at forces. A couple different forces they deal with. They deal with the gravitational force, and then friction, and then weight. The gravitational force describes forces between two objects of mass, m1, m2, separated by a distance r. That gravitational force is equal to g times m1, m2 over r squared. Where g here is a constant, 6.67 times 10 to the minus 11 is equal to our constant g. Those will be given to you in the MCAP, in your passage problems. They'll give you those types of constants. But you do need to know, and in fact, if you look on page 15, they have an example that they work out. Notice how they take this and they express it in fractional form, where 6.67 they represent as 20 thirds, right? Because 6 is 18 thirds and 6.67 is 2 thirds, so it's 6 and 2 thirds are 20 thirds times 10 to the minus 11. And then if you look at that problem on page 15, notice how they work through the problem, and it becomes a lot simpler when they deal with the fraction. So that's a good indication of you to how to sort of simplify the numbers in these problems. So that describes the forces between them. Notice these are equal and opposite forces. We'll see that in Newton's third law as well, that you have these equal and opposite forces. I think that's all on that topic. Oh, one other thing. If I'm on the surface of the Earth, here's me. I know that my weight, which we'll get to, is equal to m times g. I also know that the force between me and the Earth is gm, mass of the Earth, divided by r squared. And these two are equal, so I can combine them and say mg equals gmm over r squared. You should be pretty quick on your feet to see that this is true, and this allows us to calculate what is the acceleration due to gravity. Because our masses cancel, then our acceleration due to gravity then is just the gravitational constant times the mass divided by r squared. We did this last year, or last semester, but you might not remember. But I've seen it pop up in several questions that you know how to do this. Okay. Friction also comes up. Remember, you have two types of friction. You have static friction. You have kinetic friction. Static, of course, is when you're not moving. Kinetic is when you are moving. Static or kinetic friction, let's do that first. Fk is equal to the coefficient of kinetic friction times the normal force. Now remember this stuff from last semester? Hopefully it's also pretty fresh for you. That kinetic friction, that coefficient of kinetic friction describes the two surfaces. So for example, rubber on wood will have a different coefficient than, say, metal on ice, which would have a much lower coefficient. It's also dependent upon the normal force. If I push down, then my normal force becomes bigger. And so notice, as I pull this thing along here, it has a frictional force, but if I increase the normal force, then it increases the frictional force by a lot. Okay, so that's one way you can increase that frictional force. That's our kinetic friction. Our static friction is Fs is less than or equal to mu s times the normal force. And we talked about what this inequality meant last semester, where, remember, the static frictional force has a certain value up to a maximum value. So if I'm pushing on something, and I push with 2 newtons in that direction, then I have 2 newtons pushing back to me in the static frictional force. Okay? It's only when I exceed the static frictional force that it moves. I mean, this is real time, but you get the idea. When I exceed the static frictional force, this value, then this begins to take the place of it, the kinetic friction. All right, so understand the difference between these kinetic and static friction. Mass and weight, we've already sort of dealt with, but weight, remember, weight is different from mass. And so, for example, I've seen some questions on practice tests that ask, if you're on the surface of the moon, how does your mass change? Does it increase, decrease, or stay the same? Your mass doesn't change. Your mass is an inherent quality or inherent quantity to you or to an object. So, math, inherent quality, yada, 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 y'all get it. If you're on another planet, your mass is the same, it's your weight that changes, because your weight is dependent upon that weight, the acceleration due to gravity. So F is equal to your mass times gravity. Notice that's different from inertia. Inertia is our mass. Weight and inertia are not the same. They're related by the acceleration due to gravity, but they're not the same. And then they also go into the center of mass. Now, they say in the book, and I've never seen a center of mass calculation in half dozen or so practice tests, something like that. Have you ever seen a center of mass calculation? We don't do it in the class either. But I have seen some sort of conceptual things, and I'll show you a question about that. But the center of mass is just where you can imagine all that mass to be located. So for example, in a human being, the center of mass is right around the center right here, or about your belly button. The center of mass of, this chair, for example, is probably right about here or so. Yeah, at some point that is equidistant to all the masses within it. All right. I think that you probably understand the center of mass intuitively, but I'll show you a question, an example of what to expect. Or of course with the MCAT, what to expect. Who knows, right? Because it changes all the time. Really, the only way to do really well on it is to know everything, and that's a lot. The good news is that I ran up percentages that students make, and it's like 50. A good MCAT score is like 50% correct or something crazy like that. So I know it feels overwhelming when you're taking these practice tests, and hopefully you've already taken some. I mean, you took some with Dr. Wayment. Those are old practice tests that we're pulling those questions from. But just be patient. Keep doing what you're doing. Every little bit that you do to prepare will help. Even if it's frustrating, not much fun, you'd rather be outside on a day like today. Okay, let's do a few more questions. Let's see. Oh, this is a good passage question. Let's see, do we know everything? Yeah, we know everything to do this one. Let's do this one. I think this was the front one. We're going to do these two questions. Nice MCAT questions. Take a minute to read it. We're going to do the top question first. I'm going to go ahead and start your deal. You're going to do this question first. So read it. Answer the question. If you finish that first question, go on to the next one. I'm going to pull it up next. So just for reference, nobody has the right answer right now, okay? So you might want to rethink your answer just a little bit, because nobody has it right. All right, I'm going to stop at 2 minutes. 2 minutes. 3 more seconds. Discuss if you don't know. All right, here we go. All right, go. Oh, seriously? Yeah, everybody had C before, and then you moved to B. But the right answer is, I can't even click it when y'all don't, nobody gets it. one up here. D is the right answer. I wish at least one person would get it right, and then I can click on the little bar. So here, remember that our kinetic friction, well, first let's just sort of explain what the passage says. I have this factory, and I want to move boxes. I'm going to drop them from here, and they're going to go down here, and then they're going to slide along from point B to point C, right? Yeah, it's going to move from point B to point C. And then I want to give an expression for the acceleration of that vector, of that object. Now, the only force acting on this object when it's moving from point B to point C is the frictional force. Because there's no forces pushing it. There are some vertical forces, the normal force and the weight there. So those are the only forces I have that are acting on the block as it moves from point B to point C. There's a lot in this thing. Like, for example, you've never seen I and J, right? You don't know what those are. We don't usually use those in the 101 class. The I vector is just another way of saying the X vector. The vector in the X direction. The J vector is just the Y vector. And they describe that, but you know, when you've never seen it before, you read it and like, wow, shoot, I got to figure out what that is too. So here, I is just the unit vector for the X direction. Now, I want to figure out now how to describe the acceleration. I know that the acceleration is equal to the net force divided by the mass. The net force in the X direction, which is really all I'm concerned about, is the frictional force, which is in the negative direction, divided by the mass. That frictional force is mu times the normal force. Remember, this is in the negative direction, times m. And so that's going to be mu mg divided by m. The m's cancel, and I have that negative. So most of you put C. That's close, but it's still not right because it's in the negative direction. Okay, let's try this next one. What physical quantity is represented by the quadrilateral OABC in figure 2? All right, I'm going to stop at 35. 35. That's awesome. C is right. It's a V versus T graph. The area is the velocity times the time. V times T, that's meters per second, times seconds. That gives me meters. If you ever face one of these, if you're looking at the area, remember it's the Y variable times the X variable. Just look at the units, and the units will tell you that you're looking at a distance. If you're doing the slope, it's the Y variable divided by the X variable. In this case, that would be meters per second, our acceleration, if we were looking at the slope. But we're not looking at the area, so C. All right? Good. Let's see. I think I have some others we can do. Let's do this one too, huh? It's a good one. Just having practice doing these passage problems will help you. We're going to start with this one, by the way. Doing these passage problems will help you sort of learn how to read them. There's some in your book as well that you can practice with their solutions. I think that's right. Okay, just a few more seconds. I'm going to stop at 1:52. There you go. Oh, let's see. We're split between A and B. Again, part of this is being able to interpret data and look at it. Here we're looking at, based on table 1, which of the following statements describes the relationship between static friction, let's see, is based on this, right? So whatever your threshold mass is here, you're putting a mass on here that causes the block to move, right? You figure out what mass you put on here to make it move. We had a similar lab experiment, remember the little cart, something like that. So I put a mass on here to cause it to move. So how much mass I put on here directly correlates with the static friction of this block. And so I want to ask myself, how does the mass, which is the static friction, correlate to base area? Notice here my mass and my base area are 0.01. And then, what does this say? Set 2. My mass here is 0.049, and I get 0.02. But notice if I make my block area bigger, my mass remains constant. Similarly with 3, I'm sorry, you can't see it very well. I was trying to futz around with it. So what would you say is the right answer in light of that, A or B? Y'all agree? It is A. A is the right answer. That the threshold mass is independent of the block base area. That's another way of saying the static friction is independent of the block base area. But in order to recognize that, you need to recognize that the mass here is directly proportional to the static frictional force there. Okay, let's try this next one. After the block began to slide, how did its speed vary with time? All right, I'll stop at 42, let's say. 42. D is right. Awesome. So notice here that after it starts moving, I then am going to have a net force acting on it. After it starts moving, the force here, the weight, will equal the tension in the string. The tension will be pulling in this direction. I'll have a kinetic frictional force in that direction. I'll have a force tension in this direction, a kinetic frictional force in this direction, but the net force will equal to that tension minus kinetic friction, and it'll be greater than 0. So that means that if the net force is greater than 0, it will be accelerating. Net force bigger than 0, so it will be accelerating, so its speed will vary with time. What do we say the answer was? Yeah, linearly with time. So if I were to plot V versus T, for example, my V versus T graph would look like that. It's accelerating at a constant rate because it has a constant force. It's going faster and faster each second, but at a constant rate it's increasing. Let's try this last one. Okay, so a few more seconds. I'll stop at 42. Very good. All right, 42. Awesome, D is right. The time that it took to slide down the board, is that the answer y'all put? Yeah, a lot of you put A. I can sort of see how you might do that, but the time that it took, what if you had a longer board? Then the time, the friction would still be the same, but the time would still be the same. Or what if you had a shorter board? the friction would still be the same, but the time would change, right? So it's not that doesn't really make sense in light of the whole longer board, shorter board argument. The distance that it goes down before coming to rest, it's just not going to do that because you're trying to measure the kinetic friction, and it has this constant force that's pulling it down. It's not going to come to rest. Mass of the board is irrelevant. No, I put that. But D is the right answer, the angle of the board. All right, let's see. I think I had a couple more we can do. Let's try this one. This one right here. Suppose that a ball is thrown. No, I'm sorry. We'll come back to that because we need to do kinematics. Okay, let's move on. A couple more little bits of information. Oh, there's my sorry, there's my thing. I was looking for that. What is this 142 up top here? Which of these represents the center of mass? This is an object, half of it's lead, half of it's foam. Which point A, B, C, or D is the center of mass of that object? All right, I'll stop at 33. 33. B is right, in fact. We know that our center of mass isn't going to be in the middle of the foam. The foam actually has very little mass at all, so it doesn't really change the center of mass at all. It's definitely not going to pull it all the way over here. So it's actually just slightly off center in the lead piece, and the center of mass is not going to be over here. Anything would be to the right of B, but it's going to be at B. I think that you have a good intuitive understanding of center of mass. We're not really going to dwell on it. But if you want to look at the equation in there, you can see that how to calculate the center of mass for a set of particles. But we're not going to do that. All right. Gosh, just 15 minutes left. Guys, I know this is fast, okay? I mean, this is like 3 weeks in Physics 101, or 2 weeks, basically. But y'all are okay? Everybody's okay? All right. Okay, let's look at, where do we leave off? We had forces, acceleration. All right, so we have Newton's laws. First law, they describe it kind of nicely, actually. I don't usually describe it in this way, but the first law says that F net equals ma is equal to 0. It says that if you have no net force, you're going to have no acceleration. If you have no net force, whatever your object is doing, it's going to keep doing that, whether it's moving at a constant speed or whether it's at rest. If you have no net force, no acceleration. The second law says that if you do have a net force, then you will have acceleration that will follow this expression. If I have a net force, my acceleration will be that force divided by the mass, or F equals ma as we more commonly know it. And then the third law is our equal opposite forces. It says that for every force we have an equal and opposite force. So if I have a force that I'm applying from object A onto object B, then I have another force that's negative that on object B due to object A. All right. Now we need to be careful, like if I just have one object sitting here, it's not like I have two forces acting on it. Instead, if I say I push on this board, I'm pushing on the board, that is A onto B, I'm A, the board is B, and then the board is pushing back on me, that's B onto A, the board onto me. Okay, and it's opposite direction. So that's the third law, these action-reaction pairs. And then also get into kinematics. And unfortunately, we're not going to be able to get very far in kinematics, but I would look at some of the practice questions over the weekend as you prepare for Chapter 2 as well. But on Monday, we're not going to do kinematics. We're going to move on into energy. I really want to get into some of the chapters that we haven't seen in the lecture, because, like, for example, we didn't do, well, we're going to do sound this year. We're going to do sound this semester, but nuclear physics we don't usually get to, and we won't. So I want to do that in this class. All right, so kinematics. They give you some equations. They're on those sheets. Some of them should look familiar to you. The V equals V naught plus AT. These are all instantaneous quantities, instantaneous velocity, instantaneous acceleration. We also have X equals V naught T plus 1/2 AT squared. And then we have this new equation, which we've never seen before, because I don't usually give it in class, which is V squared equals V naught squared plus 2A times X. This just comes about, really you just have two kinematics equations. This comes about by substituting one into the other, and you can solve for this equation. That's why we don't do it in 101, but it's a useful equation to know, because it does help you to figure out some scenarios, and hopefully we'll get to some questions like that. But if not, you can look in your practice questions, and you'll see kinematics problems where that's relevant. I'll try to pull one up. And then we have another just definition, is that X is equal to the average velocity times T. We've used that before. If you have constant acceleration, that's true at all times, because your average velocity is equal to your instantaneous velocity. Alrighty? Projectile motion, you know what? I read an article recently and they said that projectile motion isn't really a big focus on the MCAT. You can see it, but it's like one of those tertiary topics. So we're not really going to look at projectile motion at all. But it does include some nice topics like vectors and kinematics. But we're not going to do it just for sake of time. But if you really want to know everything for the MCAT, then you might want to look at projectile motion. But as I understand it, don't take my word for it, but I mean, yes, I read an article and it said this. It wasn't a quack. It said that projectile motion is a tertiary topic on the MCAT. So it's fairly in-depth, and a lot of students have trouble with it, so we're just going to skip projectile motion. So instead, let's just do some problems with kinematics, linear 1D kinematics. What's a good one? I'm not going to be able to do them all, so let's just pick a couple. Let's do this, suppose that a ball is thrown. So on the page with the vectors, the one in the lower left, suppose a ball is thrown vertically upward from the earth with velocity v and returns to its original height in time t. If the value of g were reduced to g over 6, as on the moon, then what would happen to t? What would happen to t in this case? Remember when we're throwing stuff up in the air that we talked about in class, when it gets to the top of the trajectory, that the velocity goes to 0. Remember, your acceleration is -10. Oh, I'm sorry, let me start the thing. All right, guys, let me just remind you. It's a really useful thing when you're doing the MCAT or doing any multiple choice test that you can just eliminate answers. So I have 2 that are increased and 2 that are decreased. I should be able to, in my mind, eliminate 2 of those, right? If I throw something up and it comes back down, if I have less gravity, is it going to take more or less time for it to go up and come down if I have less gravity? it will take more time. So here, the time would not decrease. That would mean it would come back down faster. It's going to increase. All right? All right, good. I'll stop at 111. Otherwise, we're pretty evenly split down the middle. It's not a trivial problem. So, as we said, it's either A or B. It has to be either A or B. But you know what? If you can get down to 50% chance, that's pretty good, I think. In a multiple choice test, if you can eliminate 2 answers, you're doing a pretty good job so far. But now we want to pick between A and B. So remember that V is equal to V naught plus AT, right? At the top of the trajectory, V goes to 0. So I can say then that T is equal to V naught over A. Or it's actually negative V naught over A, but A is negative, so the negative goes away. So I'm just going to get rid of that negative so that we're not confused by it. So what happens now, this remember just is time for half the trajectory. Turns out it doesn't really matter. What happens if I decrease A by a factor of 1/6? How much does T increase by? 6 or 6 to the half? 6, right. So if I have a 1/6 in the denominator here, then it's going to be 6 over here. This is the 6 to the half. That's the square root of 6, right? Yeah, so that's just the square root of 6. All right, so A is the right answer. All right. Let's try 61 here. In this one, just a little hint, you're going to have a couple steps. You're going to need to also split it into 2 pieces. Because you have, you're moving from, you have one time when you're moving in one direction, and then another time when you're moving in another direction. I'll know the total distance that it travels. Right, no. Were you using a calculator? You are? Yeah, you want to move away from that. You'll find that if you sort of wean yourself off of it, it'll be easier. You won't be able to use a calculator in the practice test I take in this class. All right. Let's just do a few more seconds, okay? We don't have long. All right, 2:15 we get out of here, is that right? It's like an hour and a half of torture, isn't it? Is it torture for you? Heather, is it torture for you? No. No, you like it. Right. Okay, stop right now. All right, let's see. Is C the right answer? Hey, it is. Awesome. So you split it into 2 pieces. The way that you do this is you first, like we're going to take it first when it's moving, it's moving at 10 meters per second, so V naught is 10 meters per second. And then V final is equal to 0, right? Because it goes 10 meters per second, it slows down to 0, and then it reverses direction. So we'll consider that first, and then we'll consider v naught equals 0, and v final equal to 20 meters per second. Is that right? Negative 20. All right, so we're going to consider those two scenarios. At first, in both of those, acceleration is equal to negative 10 meters per second squared. So the first step will just be to find the time. So remember that v is equal to v naught plus at. So time is equal to v minus v naught over a. So let's just find the time for this first one. That time is going to be v minus v naught, 0 minus 10 divided by negative 10 is 1 second. Down here it's going to be t is negative 20 minus 0 divided by negative 10 is 2 seconds. So I have 1 second traveling the first time, 2 seconds traveling here for 3 seconds total. But then I have to find the distance for both of them. And so I say x is equal to v naught t plus 1/2 at squared. V naught is 10 times 1 plus 1/2 of negative 10 is negative 5 times 1 squared. That's 10 minus 5, which is 5 meters. So that's the first round. In the second round, I do a similar thing. I say x is equal to v naught times t, which is 0, times 1/2 at squared, or plus 1/2 at squared. That's 1/2 of negative 10 times 2 squared. That's 5 times 4, which is equal to negative 20. But it's asking for the distance that it travels. So it travels 20 meters, and it travels 5 meters. So it travels a total distance of 25 meters. Now, if it asked for displacement, you would have a different answer. If it asked for displacement, it would be 15 meters, or negative 15 meters, actually. All right, because I'm traveling negative 20 and 5, I add those two together, keeping the negative sign for the direction. I get negative 15. Okay.
I used the other formula, I still have the same answer.
Oh, did you? Can you do that? I'm not sure if that was what. Let me think. Yeah, you can do that. Yeah, see, you see what she did? That makes it a lot easier, actually. Well, sorry, I showed you the hard way. So you say that v squared is it v squared or v naught squared? Yeah, that's right. So v squared is our final. That's going to be 20 squared equals v naught squared, which is 10 squared plus 2 times negative 10 times x, which is what I'm looking for. Gosh, this is a lot easier, isn't it? Does this work, really? So this is 400 minus 100, so that's 300 divided by negative 20. Oh, wait, no, you have to do it in 2 separate pieces. Because this gives you, that's not how you did it, is it? You broke it into 2 pieces?
Well, I made that 2ax the subject, and then since it was negative, the 2 was in the negative direction, and that was positive, so I had to like.
Okay. Oh, I'm sorry, we're off. Right. Okay. Yeah, I guess that. Right. I'm sorry, we're out of time. So listen, read chapter 2 next time. Do y'all have any kind of book for this class? You don't have books for it? You do have the book, you didn't bring it today? Heather, do you have it? No? Okay. You have, read up on work experience. If you send me an email to remind me, I'll send you a chapter online and a book that you can find. Also, I have a ton of screencasts and stuff for practice problems. If y'all want to see it, I'll put it on the website. I know you have a ton of other things, like this class is probably not that important to you, but it is important that you do well. It's going to be a big deal like getting into med school. And I want to see that happen. I know they tell me to shoot right. Okay? So, put some time into it is what I'm saying. Y'all have a great weekend. Get some rest. Have a good time.